Okay, cool. Thank you.
Thank you. So yeah, my name is Jirka Kremser. I work for Red Hat on a project called Reanalytics.io, and we empower developers to build their intelligent applications. So today I'm going to talk about blockchain analysis and also about processing of graphs in Spark. And yeah, so this is the outline. First, I will describe briefly blockchain because it's just 30 minutes, so it will be really brief. Then how to represent the blockchain transaction as a graph. Then how to tackle this graph from Spark perspective. It will be slightly relevant to the talk from the Neo4j guys about this open cipher. And substantial part will be the demo. It will be half of the presentation. So hopefully it will work. Because I've tried an hour ago and it didn't work because of IPv6. So I hope I will be more lucky. So yeah, the room is crowded. I guess this is because the blockchain and the hype around it, it's everywhere, right? Unfortunately, the price went down, I don't know, 2 days ago because it's still very volatile. Honestly, I don't care about the price. I don't care about the market. All I care about is the tech, and I'm gonna describe how it works. You know, I'm not gonna influence you if you should buy or sell. It's not my business. So what it is, it's distributed ledger system. It tries to create distributed consensus, which is a segue to the previous talk, right? But when it comes to data structure, it's just the linked list of blocks. So as you can see, there's one block, and there is a link to another one, and another one, and each new block has the reference to the previous one. So it's basically linked list, single linked list. The trust stems from the so-called Merkle trees. That's hash-based structures, and something called mining. Mining is, they also call it proof of work, and it's an act of lending your computing power to ensure that the system or the network behave correctly. To make it more clear, people tries to find a nonce, which is a piece of random data that is then put to the block, and if it is hashed with 256 hash function, and the result targets is lower than some number, some threshold, they call it difficulty, we succeeded and we find a new block, and we are rewarded by the network by some bitcoins and also all the fees that were in the block. This is the detail of one block. So as you can see, or not, it's very small, there's something called magic number, which identifies the network, because it's not, I'm going to talk today about Bitcoin blockchain, but there are different flavors of Bitcoin, of blockchain, and this magic number identifies the type of the blockchain. There are also blockchains for Namecoin. This is very similar to Bitcoin. So if it is relatively similar, it can be identified with this magic number. If it is different cryptocurrency like Ethereum or I don't know, IOTA, it is completely different architecture for the trust. So these are, I would say, like more diverse from the blockchain than some more similar. There's also something called the Merkle root. This is the hash of everything in there, and the nonce. This is the part that was used for solving the block. So, and today each block has a hard limit of 1 meg. It's relatively small, so only limited amount of transactions would fit to the block. And miners basically favors those transactions that put more fee for more fee for miners, because when you create a new transaction, it's up to you how much the fee should be. So if it is like a small number, it would take ages to get to confirm. So in traditional banking system, the conventional banks, if I want to send money to someone, my bank basically holds my account, my balance, and it checks if I have enough money for the transaction. I don't know the details, but I think it's stored in some relational database like Oracle or something, and then it will subtract my money and send it to someone else. In blockchain, it's completely different. If Alice wants to send some money to Bob, she has to basically spend all their money, and there is implementation details so they can send the rest of the transaction back to her. So there is something called input, so she will create a transaction with one input and two outputs. And as you can see, there is output that has address back to her, so there's a self loop. She has to spend all their money, but she's allowed to send her money back to her. And so yeah, there is a simple rule that sum of all the inputs has to be equal or higher than sum of the outputs. It's higher. What is higher that I mean, if we subtract some of the inputs, outputs, and some of the inputs, the difference is the fees. It is the fee of the transaction. So, and as I mentioned, the confirming is finding the nonce for the block. So as here in this example, Alice is trying to send 2.0 bitcoins to Bob. So he said that he doesn't have any bitcoins. If the transaction is confirmed, now he has balance 0.2 bitcoins and Bob is happy. So this is happy Bob. This is transactional in more general case, because before we had just one input and two outputs, but it doesn't have to be this way. In this case, we have three inputs, and as you can see, there are reference the unspent output from previous transactions. So this is basically the graph of the all transactions. Each input has to be connected to the previously unspent output, and by referencing it, we basically spend it. One thing I didn't mention, that miners have to also verify that the guy is allowed to do the transaction, because all the addresses are fingerprints of public keys, and he has to prove that he owns the money by his private key. But now, how to represent it as a graph? Because we can have multiple input and multiple output transactions. It's hard to say which address sends money to whom. So my first shot was to create bipartite graph when I connected all the inputs with all the outputs. And I use this representation for one of my notebooks when I'm calculating page rank, because that's all I need. I have also different representation I will show in the next slide, which has more details. So I use Apache Parquet as a format because it's suitable for Spark. Spark can open those Parquet files. It supports partitioning, so I can put different piece of data on different nodes. And it also has schema, and it's columnar, so it's suitable for this NoSQL or distributed processing. Right, and I've also developed an application called Parquet Converter. It's based on other open source project, and what it does, it takes the binary files you have on your disk if you have official Bitcoin client. If you run official Bitcoin client, it downloads all the universe. It's 280 gigabytes, and you can use this converter to run it and create this Parquet representation. So ideally, I would have some network and run some analysis on top of it. So this is the other approach I have chosen. I use it also for the other notebook, and here I have more information. I have nodes of addresses, nodes of transactions, and also nodes of blocks. So I have information in which block the transaction appeared, and also I have amounts of satoshis that were sent in the network. In the previous representation, I have only edge that some address was communicating somehow with the other address. Here I have more information. I'm basically capturing these multi-input and multiple output transactions. Right, so how to tackle graphs from Spark? There is pre-built library or module called GraphX, and some external one called GraphFrames. You have to put some jar files on class path to be able to use it. So I have two notebooks, and one uses GraphX and the other one uses GraphFrames. There is a couple of built-in functions in Spark, for instance, for label propagation, page rank, counting triangles. But it's extensible. It supports something called Pregel, which is a toolkit, declarative toolkit, where you can describe as something called superstep, in which you say it's iterative method, where you specify that you accept messages from the neighbors. You update the state, and you send those messages to your neighbors. And in this iteratively approach, you can achieve something pretty complex algorithms. And there is a language in graph frames. There is a language called Motif, and it's inspired by Cypher, but it's not as powerful. But it's there. So, as if you were here on the lecture about Cypher, you will probably know more than I. So this is the basic architecture of Spark. For those who are not familiar, it's ETL toolkit or framework. It stores everything in memory, if not said otherwise. It also supports of heap memory. And it has a lot of bindings to other languages like Python or R, so it's suitable for data scientists. It's written in Scala, so there is native support for Scala and Java. And the architecture, so there is always something called driver program that holds the application, and it communicates with the master node that coordinates all those workers and schedules the work to those executors. So executor runs on worker node, and it runs those tasks. So yeah, talk is cheap. Let's do the demo. Oops. Is the font visible? Should be, right? So what I'm gonna do, I have a cluster that contains OpenShift, and I'm gonna create a new Spark cluster there. So I'm gonna use something called Oshinko. It's an open source library we develop, and I'm gonna deploy a new cluster. I will make 2 workers and call the cluster FOSDEM. And here, sorry, oops. Here I have the OpenShift console, and I can see there is nothing there. Yeah, there's nothing there. So if I run the command, it should start deploying the cluster. As I can see, there is one master deployed for me and 2 pods of worker. By the way, OpenShift is similar to Kubernetes, but it supports additional features like security templates. But it's very similar as Kubernetes. Actually, Kubernetes is running under the covers. So now the cluster is up and running, and I can deploy my my notebook application, Jupyter Notebook. To do that, I will use new app. This is OC is OpenShift client. So I'm deploying my Docker container, but it also supports these OCI containers by CRY-O. But here I have to specify the name of the master, so I called it FOSDEM, right? So if I do that, it will deploy the Spark, the Jupyter Notebook. What I have to also do is to expose the root, because by default, if I deploy something to OpenShift, is not exposed. I want to make it visible for the external world, so I'm exposing the root. And by the way, I can do the same from the web console, and also we have a web-based application for deploying those Spark clusters. But I wanted to mix it, you know, as you can see that I can do something from the command line, and it does things in the web UI. So now the root is exposed, so I can go there, and it doesn't work. I can check if everything is up and running by get all. Yeah, it looks good. No. The container is still creating, so probably it's pulling the container. I can kill it. It sometimes helps. Because Kubernetes or OpenShift tries to assure that there is at least one, in this case, one instance of running pod. And if I kill it, it tries to spin a new one. So probably the previous one, yeah. And so I kill the previous one, and the new one is now deployed. So if I go to this page, now it works. So this is the Jupyter Notebook. Previously, you may have seen the Zeppelin Notebook. These are different. This is more famous one. And yeah, so now what you can see here is a Python. I can hide this. Oh, unfortunately, I can't hide the top bar, so it's relatively low on the page. So I can check if we are connected to the external cluster, and yeah, we are. I can also create or open the Spark UI console and check if there is application attached to this cluster. And sorry, where? No, should be right here on the master. Yeah, this guy is the UI root. It's the console for Spark itself. And as we can see, there is one application connected to it, and it runs for 45 seconds. So this is our driver application, is the Jupyter Notebook. So now if we evaluate these cells, these are sent to the Spark master, and Spark master schedules them to the workers. And once it receives the answers, it puts it back to the driver, to the Jupyter Notebook, and we can see them. I also need to change this guy. So now what I'm doing, I'm reading these Parquet files, which I have prepared before, using that Parquet converter. You know what? Let me run all the cells, and I will describe them when they're evaluating, so it will be faster. So what I'm doing here, I'm reading those Parquet files with nodes right here, and the code is available on GitHub. I will give you the link at the end of the presentation. So I'm reading all the addresses, all the transactions, all the blocks, I think, yeah, and mixing them together because this is the GraphX technology. It expects all the nodes in one big data frame. So I'm merging them all together and putting this discriminator column called type. This is implementation details, and this is only a fraction of the blockchain network. This is not whole blockchain because it wouldn't be feasible to do it in reasonable time. So as you can see, we have 4 million of nodes. I think it's transaction for a couple of days. But the framework scales. You can use the same approach for the whole blockchain if you have enough time. Yeah, so I've evaluated. Here I'm creating the graph representation in GraphFrame. Sorry, I've mentioned this is GraphX, is actually GraphFrame. Sorry, this is GraphFrame. So under the covers it uses data frames, not the RDDs as a GraphX framework. So here, for instance, I'm calculating in degrees and out degrees, and creating some basic statistics like standard deviation, average, and standard deviation and average for each type of nodes. So for instance, for type T, this is the transaction, we have average degree, in degree is free nodes, free edges. So in other words, each transaction has in average free incoming edges. This is the example of the motif language, so it is pretty similar to Cypher, but for instance, I can't create or specify these paths. I mean, reachability on some kind of edges. I can specify only just one edge. I can't create, transitive closure or anything like that. It's very simple. I can create those patterns. So for instance, if there is address and there is edge to transaction, and here I will specify what the address actually means. So address means that there is a type that equals to A, and I can specify if the value on the edge is lower than 10,000 Satoshi, and on the outcoming edge from the transaction is also lower than 10,000 Satoshi, and it's somehow time windowed because I have the reference for the block, and on the block I have a timestamp, so I can specify the time frame for the query when it happened. So these are the results for quite complicated query. And I can also visualize piece of the graph because it's really huge, and it wouldn't be nice if I showed everything, but I will do it anyway at the end. So this is the one transaction visualized. So this is the green one is the input of the transaction, and the red ones are the outputs. And the nice thing about Jupyter Notebook is that it's interactive. I can plug in pretty arbitrary transaction ID right here, and it would work. It would visualize the different transaction for me. So yeah, at the end of the notebook, of this notebook, I'm using NetworkX library. It's a Python library for graph visualizing or processing, and I will visualize the same transaction with graph or network X, but it's not as nice. I can show the labels, and it's even worse. And before this library, like this one, it's called Sigma.js. It's JavaScript library for visualizing the graphs. I could have also used D3, but put a more effort to it. But this is like out of the box working, the Sigma.js. So yeah, and here in this case, I'm trying to visualize like bigger portion of the graph. It takes 0.0004 like random sample of this fraction, and randomly visualize it. Yeah, it's really messy. So this is the graph frames notebook. I've got also different one, which is called based on the graph X. So let me deploy this one. Oh, and the Docker containers are on Docker Hub. I need to expose the root for this one as well. So this one will use a different notebook technology, actually. It's called Spark Notebook, and should be accessible under this URL. I will use Firefox for this because they have some issues with Chrome. So yeah, this is similar concept, notebook technology, but this time we use Scala. It's different binding, different language. And I will evaluate everything and describe what it does. This time I'm using this representation where each address is connected to each other address, but there is no other information like blocks, transactions, or even values on the edges. It's because I'm gonna run the PageRank algorithm, which is prepared in this library, and I don't need this information. It's faster. So yeah, I'm massaging the data. I'm cleaning because it contains some prefixes, so I can remove them. And this is Spark, and I'm using RDDs. This is different concept than graph frames. It's called resilient distributed datasets. It's like lower level. It's not optimized by this Catalyst optimizer as data frames, but it's in a way it's more powerful. And yeah, so right now the evaluation of this cell is running. It's calculating the page rank. So for each address, it tries to find its rank. I guess it's not necessary to introduce page rank, but in a couple of words. It's an iterative algorithm that this is the result running of page rank on some very small graph. It tries to put higher rank on those nodes that have more incoming edges, but at the same time, if the node has high rank, it contributes more to the other nodes into which he points. So in each step, it tries to update its rank, and it's a form of eigenvector centrality measure. It tries to simulate like random work through the graph, and if we randomly stop the state, what's the probability that I would end up in this node B, for instance? It's quite high, but this node has also high probability, even though there is just one incoming edge, and it's because of the fact that there is a loop from this highly ranked node. Yeah, it's sorry?
What are these nodes?
This is arbitrary nodes. Like
yeah, I see, but I mean, it's 40%. I don't fully understand, but that seems to me there's a high probability a transaction ends up there. So what kind of nodes would have that property?
Yeah, this is the random graph on which I want to explain PageRank, and yeah, it doesn't make sense for blockchain. And actually, once this PageRank will finish, the results, the ranks are not actually probabilities. These are like random numbers because they are higher than 1. But I can represent them as a probabilities by summing everything and normalizing it. All I need is to rank those addresses by this PageRank and see if the highly ranked nodes, addresses in the network, are somehow interesting. Yeah. Before I tried it, it took 2.5 minutes, still calculating. So yeah, it just finished. And as you can see, there are, for instance, this one has higher probability or higher rank than one. So here I'm sorting them by their rank, and in this notebook I can actually query external websites. So I will be querying the blockchain info for fetching additional information about the nodes. It is because I have only a small portion of the graph, and for instance, I want to have like the overall incoming transactions and overall outgoing transactions from the address. Like how many bitcoins does it receive for all the time or send. And I wouldn't be able to reconstruct it only from this small fraction of the transaction graph. So that's why I'm a little bit cheating by querying external site for this. So yeah, I will be kind of augmenting this output with HTML. Sorry? Sure, yeah.
Maybe I missed one. What are the benefits of visualizing the transaction?
So what is
the main benefit of visualizing the transaction?
Yeah, what I have right now is a framework for working with blockchain data. Main benefits could be, for instance, you can use this framework for identifying similar addresses in a network. Because as you may know or not, the Bitcoin or blockchain is a pseudonymous network. We can see all the transactions of each address, but we can't be sure who is behind this address. But if we can somehow inspect, see the behavior of some certain address, we can cluster them together and say with some kind of probability these are the same or not. This is just ideas, you know. And
It's more like a data analysis.
yes. It's not very useful. This is just for demoing OpenShift, and you can use our technology, which is also open source, and you can do it on cloud. It's pretty convenient. So this is a sorted list of these Bitcoin addresses by this PageRank, and there should be also a link to the external site, in this case blockchain info. As we can see, we just found a mining pool called Fish Pool. So just by looking into the graph and its topology, we are able to identify kind of significant address in a network. And by the way, these mining pools are entities in the Bitcoin network that serves for miners to obtain more often less amount of money, because it's highly unlikely that it will be you who will confirm the transactions, so they aggregate into those mining pools, and these mining pools reward those members by doing that work. If the mining pool succeeds to find a new block, it will reward all these members who are mining in this period. Okay, yeah, 10 minutes, that's fine. So I can see if there are some other interesting one. Now this is, for instance, in this case, we don't have any information, and we had the information before because the phishing pool itself put this information into the blockchain info. This is not some magic not any magical was happening. As me, I have also my Bitcoin address, and I can go to blockchain info, I think /text, and I can put some metadata on my address if I want. Yeah, this is different one. This is, for instance, this one is a hot wallet, so this is like wallet in browser or in online, and they want to be identified. It makes sense that they put this tag on their Bitcoin address. And here you can see it actually starts with one fox, that hash, and actually finding this address is also difficult task, because they have to spend a lot of computer power to come up with a pair of private and public key, where the fingerprint of the public key starts with one fox.
This was 4 million transactions, right? This is a subset of 4 million transactions.
Sorry?
This was the subset of 4 million transactions, right?
Subset of what?
4 million.
Yeah.
Okay. So you have 4 million.
And as you may see, this is the total number of received or total number of sent of these addresses, and this is the resulting or the current balance. For instance, this address received a huge amount of money, but the balance is 0, and it makes sense if it sends everything what it received. So yeah, these are the notebooks. They are on the GitHub repository. Let me switch back to the presentation. So key takeaways. Blockchain is out there. Its format is open. You can dive into it. You can see what's there. You can use my framework to convert it to the graph and process it further. This is just starter. You may do a lot of more interesting work. There are two different technologies in Spark. One called graph frames, one called GraphX. I had bad luck with graph frames, for instance, running the PageRank algorithm. Not sure why it was working for relatively small graphs, but once I've achieved some threshold, it didn't work. Like I had a lot of out of memories, even on relatively high memory platforms. I think it's really important to create reproducible experiments if you are in data science community, because what happened to me, I read some scientific paper and they have some data set that is publicly or is achievable in some zip file or somewhere, and it's relatively hard to reproduce their work. If you put it into the containers and you create these notebooks, it's pretty easy for other guys to extend your work. And as always, like good representation may be crucial. So yeah, please visit our website redanalysis.io. I will also put some stickers right here if you want some. And yeah, this is my presentation. If you want to download it, I encourage you. So.
Any other
Questions?
questions? For Jay? Yep.
Is it doing the streamline mode, like taking data from the ledger directly? And,
No, it's not streaming. Yeah. So the question was if it is doing the streaming mode. No, it's just batch processing. I want to improve it by streaming.
It's more advanced.
Yeah.
If it's a streaming case, then is it security-wise, is it okay? Because
Yeah, I want to improve that in that way. It's relatively difficult because I can't do it using this binary data stored in the system. I would have to run the Bitcoin daemon and hook to it using JSON RPC and trying to see the new transaction and visualize them using Spark. How is it called? Streaming. Yeah. It's something I want to do.
Cool. Other questions?
Yeah. You what?
Was that one diagram that you showed a single transaction with such a large number of outputs?
Yeah, it was. Yeah.
Is there any insight into why one transaction would have so many outputs?
It is.
In such a large number?
It is because I can show you the notebook again if we have time. I actually find it in a way that firstly I calculated the output edges of each transaction and I sorted them by the output edge and I took the relatively high in the list. I can show you right here. It's sorted by out degree and I'm taking the 8,000 one. 800 one.
Transaction to show because it is unusual.
Exactly.
I see.
If I pick random one, it will be just a couple of outputs and a couple of inputs. Yeah.
Okay.
Exactly.
Thank you.
Good question.
Okay, cool. Thanks a lot. Yuri is also around, I think.
Sorry?
Are you around today? So,
Yes, I will be here.
So
You
if
can
you
catch me
have
later.
other
Yeah,
questions,
sure.
feel free to reach out to him. And next presenter will be Hannes talking about G-Core, a new graph query language.